Picture this. It's the absolute dead of summer. We're talking about that kind of heavy, relentless heat that just, it radiates off the pavement and seems to just seep right through your walls.
Yeah, the kind where you start sweating the second you step outside.
Exactly. So you're sitting at home, finally settling in, and you hear that beautiful, familiar sound, right? The air conditioner kicking on.
Best sound in the world on a day like that.
Right. And you feel this tiny, promising puff of cool air from the vent. You take a breath, you're waiting for the relief, but then almost immediately, just click, it shuts off.
Oh yeah, that is not what you want to hear.
It's the worst. You sit there sweating, wondering what just happened. A few minutes go by, and it happens again. On, off, on, off. Your house never actually gets comfortable. The air feels thick, and frankly, it is driving you completely crazy.
I mean, it's an incredibly frustrating experience, and it's something homeowners battle constantly without really understanding the mechanics behind it.
So we're not just going to complain about it today. We're going to fix our understanding of it. That maddening on and off phenomenon is called short cycling. And today's deep dive is all about decoding what your system is desperately trying to tell you when it behaves this way.
Because it is definitely trying to tell you something.
Right. We've pulled together manufacturer troubleshooting guides, advanced HVAC textbooks, and decades of maintenance logs to really explore how the equipment actually works behind the scenes. And more importantly, we're going to look at exactly what you can safely check yourself before you have to call in a professional.
Which is a lot more than most people think, honestly.
Exactly. And to help us navigate these mechanical mysteries, we have the perfect guide. Joining us for this deep dive is Dave Hartzell of Hartzell's Heat and Air in Kingfisher, Oklahoma, a NATE-certified master HVAC technician with 47 years in the trade.
Glad to be here. This is a topic I'm incredibly passionate about because, well, your system is constantly communicating its physical state to you, provided you actually know how to listen to the symptoms.
Let's start with the stakes then. When a system is short cycling, clicking on and off like a confused metronome, what's actually happening to the environment inside the home? I mean, why do we care, aside from just being hot and annoyed?
Well, to understand the failure, you really have to understand the goal of a healthy system first. An air conditioner's job isn't just to lower the ambient temperature. That's only half of it. It's also a high-powered dehumidifier.
Wait, so it's actively pulling water out of the air?
Exactly. A properly functioning system is designed to come on and run for a long, steady, uninterrupted stretch. It needs that sustained run time to pull the ambient temperature down and to physically wring the humidity out of the air inside your home.
Okay, so if it's cutting on and on.
Right. A system that short cycles simply never runs long enough to pull that moisture out.
So the air might drop a couple of degrees, but it keeps all its water weight.
Yeah.
That explains why a short cycling house feels like a damp cave.
Yeah, that's the first major impact. Your house stays warm and incredibly sticky. But the second, and arguably more critical consequence, is the immense physical toll it takes on the machinery itself.
Let me ask you about that mechanical strain. Is it kind of like driving a car and grueling, bumper-to-bumper stop-and-go traffic versus just cruising down the open highway?
That is a really good way to look at it, actually.
Yeah, because when I'm on the highway, my car's engine is just hunting along.
Yeah.
Everything is lubricated. There's minimal stress. But in stop-and-go traffic, I'm constantly hitting the gas, slamming the brakes, shifting gears. The startup feels like the hardest part.
That's a great way to conceptualize the mechanical stress, because the hardest, most demanding moment on any heavy mechanical equipment, especially an air compressor, is that initial startup.
Just getting it going.
Right. The compressor is taking a massive electrical and mechanical jolt every single time it tries to overcome inertia and start spinning.
Wow.
So if your system is stuck doing that, say, 50 times a day instead of 10, you are forcing that compressor to absorb an incredible amount of kinetic and electrical wear, which, leads directly to premature equipment failure.
So we definitely know the stakes. We know it leaves us sweating, and it physically batters the machinery. I'm looking at these troubleshooting guides, and a lot of them point straight to the thermostat as the first suspect.
They do, yeah.
But I have a hard time believing a perfectly good heavy-duty AC system would fail just because of something happening in a random hallway. Like, if I install a massive, top-of-the-line 5-ton cooling unit, shouldn't it just overpower whatever heat is near the thermostat and cool the whole house down?
Let me stop you right there, because that brings up the bigger is better myth, which is honestly one of the most destructive misunderstandings in residential HVAC.
Really? Bigger isn't better?
Not at all. It all comes down to thermodynamics and what we call the thermostat bubble. A thermostat doesn't know what the temperature is in your bedroom or your kitchen. It only reads the air immediately surrounding its own casing,
Wait, just that tiny little area?
just that tiny bubble. It assumes that little pocket of air perfectly represents the entire thermal mass of your whole house.
Which is a pretty massive assumption for a little piece of plastic on a wall.
A huge assumption.
Mhm.
So let's take your scenario. You put a massive, oversized air conditioner on a moderately sized house. Yes, it produces a tremendous volume of cold air very quickly. It blasts the air out of the vents.
Okay, sounds good so far.
But if one of those supply vents happens to be anywhere near the thermostat, it gets blasted with freezing air. Within 5 minutes, the thermostat's little bubble drops to 65 degrees.
Oh, I see where this is going.
Yeah, the thermostat thinks its job is done and it completely shuts the entire system down.
It thinks the whole house is cold. But what about all the couches, the floors, the walls?
They are still holding all their heat. The thermal mass of the house hasn't changed at all, so the oversized system slams off, having run for only 5 minutes, meaning it pulled zero humidity out of the air.
And then what? The heat just seeps back out.
Exactly. 10 minutes later, all those warm walls and furniture bleed their heat back into the room's air. The thermostat's bubble warms up, it panics, and it kicks that massive system right back on.
Yeah.
An oversized unit is fundamentally doomed to short cycle because it satisfies the air temperature way too quickly without addressing the thermal mass or the humidity.
So I could be driving myself crazy trying to, fix a machine that's actually functioning exactly as its oversized dimensions dictate it must.
Right. And you can also have the opposite illusion. If your thermostat happens to be hanging on a wall that gets hit by direct afternoon sun, the sun bakes the plastic, warms up that pocket of air, and the thermostat kicks the system on, thinking the house is boiling when it really isn't.
So it's getting tricked.
Exactly. You have to play detective in your own hallway. Look at what is physically around your thermostat. Is a lamp cooking it? Is a vent freezing it?
Okay, so let's say the thermostat environment is perfect. No sun, no drafts, and the system is properly sized for the house's square footage. Moving down the troubleshooting list from these maintenance logs, the next major section is all about static pressure and airflow.
This is a big one.
Now, I know the air filter protects the delicate coils from getting caked in dust. We all know we should change it. But how does a dirty filter actually cause a heavy-duty machine to just give up and shut off?
You have to think of your system as a breathing machine. It requires a constant, highly specific, unobstructed volume of air moving through it to survive.
To survive.
Literally. When you neglect the filter, it stops being a dust catcher and becomes a solid wall of dirt. This drastically alters the static pressure inside the ductwork.
So if the static pressure changes and the system is suffocating, is it kind of like trying to run a marathon while breathing through a heavy winter scarf? Like the machine physically just gives up to catch its breath?
That is the exact mechanism at play. When the system is starved for air, the centrifugal blower motor creates a vacuum trying to pull air through that blocked filter.
It's pulling as hard as it can.
Right, it starts working twice as hard, drawing higher amperage. And because it's working so hard, the motor itself generates excess heat. At the same time, the heat from the machinery isn't being dispersed by the airflow because there is no airflow.
So it's just baking itself.
The system physically overheats inside the cabinet.
But it doesn't just burn up and catch fire. It shuts off.
Right, because modern systems have internal high-limit safety switches. These are thermal sensors designed to prevent catastrophic failure or a fire. When the internal temperature spikes because of that suffocated airflow, the safety switch trips and forces the system to shut down to cool off.
Even though the thermostat in the hallway is still screaming for cold air.
The safety switch overrides the thermostat. Safety always comes first. So the machine sits there, off, cooling down. 20 minutes later, the switch resets. The machine tries again, immediately suffocates against that dirty filter, overheats, and shuts down again.
And there is your classic short cycle.
Exactly.
This is where the physics get a little confusing for me, though. A dirty filter starves the system, overworks the blower, and overheats the motor, causing a shutoff. I get that. But I was reading an HVAC textbook earlier that said a dirty filter can also cause the system to literally freeze into a solid block of ice in the middle of a 100-degree summer.
That happens all the time.
But how? How can the exact same clogged filter cause the system to overheat and freeze solid?
It sounds like a paradox, I know, but it comes down to how thermal transfer works in the refrigerant cycle. Inside your indoor unit, there is an evaporator coil filled with extremely cold refrigerant. The entire purpose of the blower motor pulling air through your return ducts is to blow warm, unconditioned house air directly across that freezing cold coil. The warm air essentially absorbs the cold, and the cold refrigerant absorbs the heat from the air. It is a very delicate thermal balance.
So the warm air is actually what keeps the coil from getting too cold.
You've got it. If the filter is blocked, there's no warm house air blowing across the coil. Without that heat load, the refrigerant inside the coil just gets colder and colder and colder.
Oh, wow. Because it has nothing to transfer the cold to.
Right. So very quickly, the surface of the coil drops below the freezing point of water. The natural humidity in the stagnant air condenses on the metal and instantly turns to frost.
And it just builds up from there.
Within hours, that frost builds up into a solid, impenetrable block of ice encasing the entire component.
And once it's a solid block of ice, it definitely can't move any air or transfer any heat.
It just fights itself. The airflow drops to zero, the refrigerant pressure changes drastically because the heat transfer has stopped, and this triggers a cascade of pressure-related safety shutoffs. The system starts cutting on and off.
If I'm a homeowner trying to figure out if this is happening right now, what am I looking for visually?
Go look at the outdoor unit. You'll usually see a large copper line wrapped in black foam insulation. If there is visible white frost or ice building up on the exposed brass valves or the copper line outside, you have a frozen indoor coil.
Even outside in the heat.
Yep, it travels all the way down the line. Indoors, you might also notice water pooling around the base of your furnace or air handler as the bottom of that massive ice block slowly drips.
So if I see ice, what's the safe, immediate protocol? Do I, grab a screwdriver and chip it off?
No, absolutely not. Never try to chip the ice away with a tool or you'll puncture the delicate copper coil and create a massive refrigerant leak. That's a huge mistake.
Good to know. So what do I do?
The very first thing you do is turn the cooling entirely off at your thermostat. Don't let the compressor run. Then, switch the fan setting on the thermostat from auto to on.
So I'm forcing the indoor blower motor to run, but keeping the outdoor cooling part off.
Yes. You want the fan to blow whatever ambient warm air is in the house across that block of ice to melt it safely and gradually. Just let the fan run, wait several hours, and let it thaw completely.
And change the filter while I wait.
Exactly. Pull that dirty filter out and throw it away. Once the system is totally thawed and dry, put a brand new clean filter in and turn the cooling back on. If it runs beautifully and completes a long cycle, you solved it.
That's a great DIY fix. But if it freezes up again with a clean filter, or if it keeps short cycling, my immediate thought, and I think everyone's first instinct, is that the system is just low on Freon. We just need a technician to come out and give it a quick top off, right?
Let me correct you there, because this is a monumental misconception. It's probably the biggest myth in the industry. An air conditioning system runs on a hermetically sealed loop. Refrigerant is not a consumable fuel.
Really?
It's not like the gas in your truck that gets burned up and exhausted out the tailpipe as you drive.
So it never actually runs out under normal conditions?
Never. The exact same refrigerant circulates round and round, changing from a high-pressure hot gas to a liquid to a cold, low-pressure gas endlessly. If your system is low in refrigerant, there is a leak.
Period.
The sealed loop has been physically broken.
But how does a leak actually cause the short cycling? Why wouldn't it just run continuously and blow lukewarm air?
It goes back to the safety mechanisms protecting the compressor. The entire system relies on highly specific pressures to operate safely. Furthermore, the compressor motor actually relies on the cold refrigerant returning to it to cool its own internal mechanical parts.
Oh, so if refrigerant leaks out, the pressure in the system drops.
And without enough cold refrigerant coming back, the compressor would burn itself out.
Which is exactly why we have low-pressure safety switches built into the outdoor unit.
Right. When the pressure dips below a safe operating threshold, that switch trips and instantly kills the power to the compressor to save its life. As the system sits idle, the pressure inside the lines slowly equalizes and creeps back up just enough to reset the switch.
So it thinks it's safe again.
It tries to turn on, the compressor pulls the pressure down immediately, it plummets below the threshold, and the switch shuts it off again. On, off, on, off.
So if the pressure is low and it's tripping switches, why can't a technician just hook up a tank, top it off to the right pressure, and leave? I mean, people do that all the time.
Because anyone who just tops off a leaking system without finding the source of the leak is just renting you a little bit of time. It's the equivalent of airing up a tire that has a giant nail in it.
You can drive on it for another day, but it's going right back flat.
Exactly. It's treating a symptom while ignoring the disease.
But what's the actual fix?
The only actual repair requires a trained professional to utilize electronic leak detectors, find the microscopic hole in the copper, braze it closed, pull a deep vacuum on the system to remove atmospheric moisture, and then recharge it to the factory specifications. A low system is a compromised system, and topping it off is a Band-Aid on a bullet hole.
Okay, so we've covered the environment around the thermostat. We've explored the physics of static pressure airflow, frozen coils, and debunked the top-off myth. But let's say I've ruled all of that out.
All right, worst case scenario.
Yeah, the filter's pristine, the thermostat is in the shade, the coils are dry and frost-free. But the machine still fires up, hums for 30 seconds, and abruptly dies. What's happening deep inside the actual mechanical and electrical boxes?
This is where we cross from thermodynamics into the electrical domain. And just like any complex machine, the components degrade over time. There are parts inside the outdoor unit that govern the heavy startup sequence we talked about earlier.
Right, the jolt.
The most common culprit for a mechanical short cycle is a failing component called a capacitor.
A capacitor? I know the word from physics class, but what does it actually do inside an air conditioner?
Think of it as a highly specialized, very powerful battery. The compressor and the condenser fan motor in your outdoor unit are massive pieces of machinery. They require a huge surge of torque and electrical energy to get spinning from a dead stop.
And the house can't provide that.
Usually no. They require more momentary energy than your standard home electrical panel can provide instantaneously.
So the capacitor bridges that gap.
It stores up electrical energy as a dielectric charge and delivers it in a massive jolt to kickstart those heavy motors.
Like a jump start every single time it turns on.
Exactly. But over time, due to extreme outdoor heat, age, and especially the internal strain of the short cycling we talked about earlier, the materials inside these capacitors break down. They lose their ability to hold a charge.
So when the thermostat calls for cooling, what happens?
The system tries to start, but the capacitor can't deliver the jolt. The compressor motor hums, strains against the inertia, pulls way too much electrical current trying to start itself, and overheats in a matter of seconds.
Wow, just seconds.
Yeah, and the internal thermal overload switch detects that massive heat spike and shuts the motor down to prevent it from melting its own windings. It tries again a few minutes later, fails, and shuts down.
That makes perfect sense. What about the actual brain of the machine? Do the circuit boards fail in a similar way?
They do. Modern systems have intricate control boards with mechanical relays and microprocessors. They act as the central nervous system, routing high-voltage power and timing the sequence of operations.
What's a glitch?
If a relay gets pitted and stuck, or a microprocessor misfires due to a local power surge, the board will just drop the signal entirely and refuse to finish a cooling run.
So if I suspect a capacitor has degraded or a control board is failing, what's my DIY protocol as a homeowner?
The protocol is firmly and unequivocally to step away. This is the hard boundary line.
Let's make this crystal clear for everyone listening. Checking a filter and holding it up to a light bulb to check for airflow. That's your homework. Looking at the thermostat's location on your wall to see if a lamp is baking it safe and smart. Spotting ice on a copper line outside, great detective work.
Absolutely.
But once you suspect the issue involves the sealed refrigerant loop or the electrical cabinet,
You step back. Those electrical capacitors can hold a lethal charge long after the main power to the unit has been turned off at the breaker.
so even if the power is off, it can still hurt you.
They can and will severely shock you if you don't know how to safely discharge them. The high-voltage electrical side and the highly pressurized refrigerant side are strictly the domain of a trained professional equipped with the right meters, gauges, and safety gear.
It's incredibly important to know where our capabilities end and where the expert's job begins. So as we synthesize all these sources and wrap up this deep dive, what is the core message we should walk away with?
The single most important takeaway is this short cycling isn't the disease itself. It is a symptom. It's your machinery communicating with you, signaling that some underlying condition, whether it's suffocated airflow, dropping pressure, or a failing electrical component, is preventing it from finishing a normal, healthy cycle.
It's basically a cry for help.
Exactly. And by taking a few minutes to safely rule out the easy variables, like a solid wall of a dirty filter or a sun-baked thermostat, you give your technician a massive head start when they arrive. You evolve from a frustrated homeowner into an educated partner in the diagnostic process.
But speaking of technicians, we want to make sure you know exactly where to turn when you hit that boundary line we just discussed.
If your air conditioner keeps cutting on and off and the easy check checks did not fix it, let me take a look. I am Dave Hartzell, Hartzell's Heat and Air, 602 South Main in Kingfisher. Family run, NATE certified, and I have been doing this 47 years. Call 405-375-4822 or book online at hartzellsheetair.com. We are at 4.8 stars with 300 plus Google reviews.
So before we sign off, I want to leave you with one final thought to mull over as you walk through your home today. Think of the airflow in your house, not just as empty space, but like an invisible river flowing continuously through every room, hallway, and duct. And your air conditioning system is the beating heart pumping that river. Every single closed bedroom door, every large piece of furniture pushed up against a return vent, and every neglected, dust-choked filter changes the static pressure and the flow of that river. What small, everyday obstacles in your own home might secretly be forcing your system to work overtime right now, desperately trying to catch its breath? Keep that invisible river flowing, keep those filters clean, and listen to what your machine is telling you. Until next time, stay cool and keep diving deep.